So, in the last lecture, we have studied the different basic ideas about the complex function. So, we have seen how we have a complex variable, and then from the complex variable, we are able to define a function f of z of complex variable. Then, in the last lecture, we have seen how to find the limit of the function of complex variable. Then we have also seen the continuity of the function of complex variable, and now we have also seen the differentiability of the function of complex variable. So, using this differentiability of the function of complex variable, we have defined the analytic function. Okay, and also we have seen the necessary and sufficient condition for a function to be analytic. Okay, now we have to take it further. Okay, so what we have seen up to analytic function. So let us see more about this analytic function. Are you able to see my screen?
Yes, sir.
Yes, sir.
Okay, so we have defined the analytic function, correct, and then we have seen the necessary and sufficient condition for the analytic function. So, what are the necessary and sufficient condition for the analytic function? Okay, so what we know is, suppose f of z be the function of complex variable. Complex variable z, then the necessary and sufficient conditions for f of z to be analytic are, so first we have seen w by wx is equal to w by wy, then w by wy is equal to minus w by wx. So these are CR conditions, or we say CR equations. Okay, so these equations, two equations are called CR equation. But we know that this is the necessary condition, not the sufficient one. And hence, we have the second condition, what we have, w by wx, w by wy, w by wx, and w by wy are continuous. Okay, so if these two conditions are satisfied, that is CR equations and the continuity of the first order partial derivative, then we say this function f of z is going to be analytic function. Okay, now what we have, if I know this CR equations and if I know the necessary and sufficient condition for the function to be analytic, okay, then we are able to write the derivative of f of z. So we have f dash of z is equal to, if I consider in the x direction, then it will be ux, okay, plus ivx. Okay, what we know is from the definition of partial derivatives, that w by wx is ux, w by wy is equal to uy, w by wx is equal to vx, and w by wy is equal to vy. So these notations we have seen in the first semester, and that's what I'm going to use it here. So I'm able to write the derivative, okay, of f of z. If I consider the x direction, then I'll be having ux plus ivx. Now, what we know is, suppose only real part is known. That means u is known. So I am able to calculate ux. But what I know is w by wx is nothing but minus w by wy. So it will be minus I uy. Okay, so I'm using CR equations. Then next I'll be having, so I'll be having f dash of z is equal to, suppose I know only v. Okay, so I'll be having here ux is equal to vy. So I'll be having vy and plus I vx. So if I know only v, okay, and we have, so what we are having here, the next, okay, so f dash of z is equal to, see, we are able to write here. So if I want to find in terms of y only, so it will be vy minus I uy. Okay, so these are the different ways to get the derivative of the function. So if you know u and v both, then you are able to find out the derivative of this function. If you know only u, then you are able to find out the derivative of this function. If you know only v, then also you are able to find out the derivative of this function, provided that this function is an analytic function. Okay, and if you know you want to find out in the y direction, so you are able to find out the derivative of this analytic function in the y direction. So here only condition required is we have f of z and analytic function. Analytic function. Okay, then we can write, if we have f of z and analytic function, then we are able to write the derivatives. Now, where this, how and why this derivatives I have given to you, where this will be used. So what I know is, I know that f of z is equal to integration f dash of z dz. Is that okay? We can get the function if I integrate its derivative. So what I know is, I can write here. Okay. So we have f of z is equal to integration f dash of z dz. So that is, I can write this in two ways. If the real part is known, so I'll be having f of z is equal to, okay, integration, what you'll be having, ux plus ivx, but here only real part is known, so I'll write minus I uy dz, or this is same as vy plus ivx dz. Okay, so this way we are able to find the function f of z. Okay, now as we know, when we have the function is analytic, so these conditions are satisfied. Okay, so let us try to show that the functions are analytic using this necessary and sufficient condition. So we'll try the first question. Okay, show that f of z is equal to z square is an analytic function, and hence find f dash of z in terms of z. Okay, so here, what is the question we have? We have a given function f of z is equal to z square, and then we have to find f dash of z in terms of z. Okay, so we have to be careful. See, I have given you the formula how to find out f dash of z in the complex plane. Okay, so that's what we have to use. Okay, and then when I want to test whether this function is analytic or not, so I need to know what is going to be u and v. Okay, so when we have u and v, then only we are able to test these conditions, and if these conditions are satisfied, then we say the function is analytic, and if we have f of z an analytic function, then we are able to find out its derivative like this. Okay, so what are the steps that we have to follow? First, separate the real and imaginary part. That means you have to get u and v first. Okay, after getting u and v, then we have to test the CR equations, then we have to test the continuity, and after that, using these formulas, we have to find out the derivative. So these are the three steps that we have to consider. Okay, so first step, separate real and imaginary part. Second step, test for the analytic function, and third step, find f dash of z if it is analytic. Okay, so if it is analytic, then only you will be able to find out f dash of z. So if it is not analytic, definitely you are not able to find out f dash of z. So let's go with the solution. Okay, so we have that f of z is equal to z square be the function of complex variable z. So what I'll do is to separate real and imaginary part that we have done in the first semester. So we put z is equal to x plus iy. Then we are able to get the real and imaginary part. So we have what you'll be having f of z is equal to. So we have here x plus iy bracket square, and hence what is the term you will be having here? So it is going to be x square plus 2ixy plus I square y square. So I can write here x square plus 2ixy minus y square, since I square is equal to minus 1. Okay, and now I can write this as the terms without I and the terms with I. So x square minus y square plus I 2xy. So this is going to be f of z, and hence I write f of z is equal to u plus iv, where u is equal to x square minus y square, and v is equal to 2xy. Okay, so this way, the first step that we have completed, separating real and imaginary part. Okay, now we have to go for the second step. So what is the second step? Second step is finding this derivatives, and we'll see that whether they satisfy CR equation or not. Okay, so let us try whether they satisfy CR equation or not. First, we have to find out what are the first order derivatives. Okay, so let us find first order derivatives. Now we consider, okay, so w by x. So we have to find out the derivative of this u with respect to x only, and when we are finding the partial derivative, the most important thing is that the other variable is treated as a constant. Okay, so let us see what we have here. So it will be 2x, then w by y is going to be minus 2y. Then I have to find out the derivative of this with respect to x and y. So I have and w by x is equal to. So it is going to be 2y, and w by y it is going to be 2x. Okay. Now once I have this derivative, you can see this term and this term is going to be same. So I have w by x is equal to w by y, and you can see this term is minus times this term. So W by WY is equal to minus times WV by WX. So what you got here? See these equations. Okay. So we have to check whether these are exactly the CR equations or not. So you can see these equations and this equation W by WX is equal to W by WY, and W by WY is equal to minus times W by WX. So you can see exactly these are the same equations. So what we can say is that is CR equations are satisfied. So here when you say CR equations are satisfied, that does not mean the function is analytic. Okay, because these are necessary conditions, not the sufficient ones. Okay, so these are necessary conditions, so that means necessary conditions are satisfied, but we need to see what is the next condition required. So the next condition is continuity of this first order derivatives. Okay, so let us try to see whether these functions are continuous or not. So we have to consider the continuity of this. So what these functions are? What these functions you see? What these functions are? What this function you see? Do you think that they are continuous? Why do you think that they are continuous? Yeah, you can unmute yourself if you are saying yes, they are continuous. Then the question is why they are continuous? Linear equation. Okay, that's good. So actually, these are all polynomials. Okay, if you can see here, these functions are continuous because these all are polynomials. There's a polynomial in x, in y. Okay, and we know that polynomial or algebraic functions are continuous. So this is how you need to identify directly that what this function is going to be and why it is going to be continuous. Okay, so yes, these functions are continuous. So we can say directly. Okay, and W by WX, W by WY, W by WX, W by WY are continuous. So here you are not required to prove the continuity, but here you should able to identify directly that these are continuous functions. Okay, so if these are going to be continuous function, then only our sufficient condition will be satisfied, and then we can say the function is going to be analytic. So yes, these functions are going to be continuous, and hence we can say, okay, hence the necessary and sufficient conditions are satisfied, hence function f of z is an analytic function. Okay, so this is going to be an analytic function. So we got this is an analytic function now. Now what is the next task we have? Okay, so if this is analytic, then we have to find out f dash of z in terms of z. And here we know we have the real part and imaginary part also. Hence, we are able to find. Okay, so to find f dash of z, we consider. Okay, so what we consider, f dash of z is equal to ux plus ivx. Okay, so here we need to see ux plus ivx. Okay, so you can see here ux is going to be 2x and vx is going to be 2y. So I have written that 2x plus I times 2y. Okay, and now we can say, so twice is common, x plus iy. And now we have to find this in terms of z. So what I can write is, this is going to be 2z. And hence we got f dash of z is equal to 2z. So we can see that, again, what we wanted to find out is the derivative of f of z, okay, in terms of z. Okay, and here we have obtained the derivative in terms of z. So here you can see in real variable case, okay, what we have in the real variable case, suppose this is going to be x. So the derivative of x square is going to be 2x. And now in the complex variable case, we have calculated the derivative. So the derivative we have calculated is going to be the derivative of z square is going to be 2z. But see how we have calculated it. So there are two ways to calculate the derivative in complex. One, by using the first principle, and second, this is another way to calculate the derivative in the complex domain or a complex set, and that's why we get this derivative here. So here we are done with this first example. Okay. So do you have any doubt in this example, or do you have any query in any of the step here? You got this all? You don't have any doubt? That's good. Okay, great. Okay, so we'll try to go for the another example. Okay, so let's see the another example. Okay, we'll go with another example. Prove that f of z is equal to sin hyperbolic z is an analytic function, and hence find f dash of z in terms of z. So we have to find this in terms of z. Okay, so now remember the three steps. First, separate the real and imaginary part. Second, test the necessary and sufficient condition. And third, find the derivative if it exists. Okay, so this is the criteria that we have to think if it exists. Okay, so we cannot guarantee that the derivative always exists. So we have to say that if it exists, then we have to find out this. Okay, so let us see. What we have is like f of z is equal to sin hyperbolic z be the function of complex variable z. So we put z is equal to x plus iy. As first we have to find out what is u and what is v. So we have, what will be having, f of z is equal to sin hyperbolic x plus iy. Okay. Now we need to know what is sine hyperbolic A plus B. So we have sine hyperbolic A plus B is equal to sine hyperbolic A cos hyperbolic B plus cos hyperbolic A and sine hyperbolic B. Okay, so this is the formula that we have seen in the first semester, and hence we can write here. So we get f of z is equal to sine hyperbolic x cos hyperbolic iy plus cos hyperbolic x and sine hyperbolic iy. Okay, so sine hyperbolic iy. Now what we know is, since cos hyperbolic ix is equal to cos x and sine hyperbolic ix is equal to I times sine x. Okay, so these are the formulas from hyperbolic functions that we have already studied in Sem 1. Okay, and hence I use this formula and simplify this. So what I'll get here, I'll get sine hyperbolic x, then cos of y. Okay, because this formula, then plus. Okay, what I have next, so this will be cos hyperbolic x, and this will be I times sine y. Okay, so this is going to be f of z, and hence we are ready now with the function u plus iv. So where u is equal to, so it is sine hyperbolic x into cos y, and v is cos hyperbolic x into sine y. Okay, so we got the real and imaginary part. We have separated the real part and imaginary part. That means our first step is completed. Okay, now test the necessary and sufficient condition. Okay, so now we consider the derivative of these two terms with respect to x and y. So w by x. So what is going to be cos hyperbolic x cos y. Okay, and remember this thing. So what we know is the derivative of cos hyperbolic x is sine x, sine hyperbolic x. Okay, and the derivative of sine hyperbolic x is cos hyperbolic x. So in hyperbolic functions, we do not have change of the sign, so it remains same. Only for the trigonometric functions we have to consider. Okay, then I'll be having w by y. So here this sine hyperbolic x remains as it is. The derivative of this is minus sine y. And now the derivative of v. So w by x is equal to sine hyperbolic x into sine y, and w by y. So this is cos hyperbolic x into cos y. Okay, and now you can see what we have here. So this is going to be, this term is exactly same as this term, and this term is minus of this term. So we get w by x is equal to w by y, and w by y is equal to minus w by x. So we can say that is CR equations are satisfied. Okay, so we can say CR equations are satisfied. Now we have to think of the continuity of this function. Okay, so we have to check whether these functions are going to be continuous or not. So if they are continuous, we can say yes. If they are not continuous, then we have to say no. Okay, so what do you think, whether these functions are continuous or not? So what do you feel, whatever the functions we have obtained, See, there are two types of functions, the trigonometric functions and the hyperbolic functions. And we have the product of these two functions. Okay, so every term is a product of this one hyperbolic and one trigonometric function. So we know about the continuity of the trigonometric function, that they are continuous. Okay, so sine and cosine are continuous. What about the hyperbolic functions? Are they continuous? Then we have to think of the product of two functions. So what do you think, whether they are continuous? So Bhavesh has figured it out. So Bhavesh says yes. What about the others? So are you able to figure it out? Okay, Bhavesh, why you think that they are continuous? Bhavesh, unmute yourself and then tell me why they are continuous. Okay, nobody else is able to figure it out. See, I have given you the list of continuous functions. So which functions are going to be continuous? So all IIT is going to be continuous. Okay, logarithm function.
Cos of hyperbolic of minus x is equal to cos of hyperbolic of x. That's why, sir, it is continuous.
No, that is the even odd function.
Sir, that's why it is continuous, sir.
No, no, no. It's not related to even odd function. So continuity is what the left limit is equal to right limit, and it is going to be the function value at that point. Okay, so then we say it is continuous. Okay, so basically hyperbolic functions, if you have studied the definition of hyperbolic function, then they are nothing but algebraic sum of exponential functions. Okay, and we know that exponential functions are continuous, and so the hyperbolic functions are continuous. Okay, and we know if the two functions are continuous, then their product is also continuous, and hence we get this one going to be continuous. Okay, so this way we have to think of the basics and then find out from the basics, and directly we have to get the result. So this is not the time now to test the continuity to find out the left limit, find out the right limit, and then think of it. So here we have to identify directly. So yes, this function, your answer was correct, but the logic that you have used is slightly different. Okay, so basically they are the algebraic sum of exponential function, and hence they are continuous. Okay, and the product of two continuous function is continuous. Okay, so yes, this is going to be continuous. Okay, so here what we have the hyperbolic function is continuous, the trigonometric function is continuous, and these are all the products of hyperbolic and trigonometric function, and that's why these are continuous ones. So we will write directly. Okay, so since w by x, w by y, v by x, and v by y, okay, are continuous. Okay, then the necessary and sufficient conditions are satisfied. So if they are going to be continuous, and yes, we know that they are continuous, hence, and right here, hence, the necessary and sufficient conditions are satisfied. So what we say if necessary and sufficient conditions are satisfied? So we can say yes, f of z is an analytic function. So this is going to be an analytic function. So our step 2 is completed, the task 2 is completed. Now we have to think of what about f dash of z. So we have to think of f dash of z now. Okay, and hence to find f dash of z, we consider f dash of z is equal to ux plus ibx. So ux that we have calculated here, so it is going to be hyperbolic cos x and cos y, and this is hyperbolic sin x sin y. Okay, so I write here, this is hyperbolic cos x cos y plus I times hyperbolic sin x and sin y. So I can rewrite this as hyperbolic cos x, hyperbolic cos I5, and plus hyperbolic sin x and hyperbolic sin of IY. So how you are able to write this? See here, what I have given you the formula. So using this, I am able to convert the trigonometric to hyperbolic, and I am able to convert this I times trigonometric sine to hyperbolic sine. So using this, we are able to convert. And then what this formula is, you remember, sorry. Okay. So see this, what you have. Okay. So if you remember this formula, then you are able to get this as, see, hyperbolic cos of A plus B is equal to hyperbolic cos A, hyperbolic cos B plus hyperbolic sin A and hyperbolic sin B. So this is a formula for hyperbolic cosine, and hence we can write this is hyperbolic cos of x plus iy. So what we know is, we know since this x plus iy is equal to z, so it is going to be hyperbolic cos of z, and hence we got f dash of z is equal to hyperbolic cos of z. So here we got the derivative of this function f of z. So this way we have completed the 3 step. So first step is to find out u and v. Second step is to verify whether the necessary and sufficient conditions are satisfied or not. And the third step to find f dash of z using CR equations. So here we have used CR equations. Okay. So that's what you have. Now the question is it that possible the function will satisfy only the CR equation and then it will be the analytic function? So as I said, no. So these are only the necessary condition, not sufficient. Okay, so let us try one example. Okay. So show that the function f of z is equal to x cube y raised to 5 x plus iy upon x raised to 6 plus y raised to 10 if z is not equal to 0. So this term is not going to be 0. See, this is going to be z. So if z is not equal to 0, then the function is defined like this, and it is 0. So if z is equal to 0, okay. So you can see that this function is continuous function. So if you put z is equal to 0, the function value is same as the limit value, and hence we can say this is going to be continuous function. Is not analytic. So it satisfies CR equations at that is equal to 0. So it is said that it satisfies CR equation at z is equal to 0, but it is not analytic. So that's what we have to prove. And this example will give you the idea that CR equations are not sufficient, though they are necessary, but not sufficient. Okay, so we'll try to simplify this, try to show this. Okay, so let f of z x cube y raised to 5 x plus iy upon x raised to 6 plus y raised to 10 if z is not equal to 0 and this is equal to 0 if z is equal to 0. So that is f at 0 is equal to 0. So if I put z is equal to 0, then this will become f at 0 is equal to 0. And b, the function of complex variable z. Now our first step is to find out u and v so that we can test the CR equations. So we have f of z is equal to x cube y raised to 5 x plus iy upon x raised to 6 plus y raised to 10. So this is equal to, I multiply x raised to 4 y raised to 5 plus I x cube y raised to 6 on x raised to 6 plus y raised to 10. So I can write this as f of z is equal to x raised to 4 y raised to 5 x raised to 6 y raised to 10 plus I times x cube y raised to 6 x raised to 6 plus y raised to 10. Okay, so this way we are able to separate the real and imaginary part. Okay, and hence I write here f of z is equal to u plus iv, where we have u is equal to x raised to 4 y raised to 5 x raised to 6 on y raised to 10 and v is equal to x cube y raised to 6 x raised to 6 and y raised to 10. So this is u and v, and now we have to test the second step. So we have to test the CR equations. So we'll see whether the CR equations are satisfied or not. Okay, so to find to satisfy CR equation, first we need to find the first order derivative. So consider w by wx. So what you'll be having? I'll be having u upon v. So what do we know? The derivative of u upon v is equal to v derivative of u minus u derivative of v upon v square. Okay, so that's what we have. So that's what we are going to use here. See, this u and v are in the formula. Okay, and here this entire is a function u and this entire is a function v. So here we have to be careful for the formula and for the terms here. So x raised to 6. Okay, I'll be having here x raised to 6 plus y raised to 10, and here this is 4x cube y raised to 5 minus x raised to 4 y raised to 5, and this is 6 x raised to 5. Okay, so the derivative of this term, and upon you'll be having x raised to 6 y raised to 10 bracket square. So w by w y. Okay, we don't have to simplify it, but we have to be careful. Okay, then what this term will be? This will be x raised to 6 y raised to 10, and this is 5 x raised to 4 y raised to 4 minus x raised to 4 y raised to 5, and this is 10 y raised to 9. We are finding the derivative with respect to y. Okay, so we have to be careful. Then x raised to 6 y raised to 10 bracket square. Again, now we have the next. So w v by w y. using the same formula, we are able to find x raised to 6 y plus y raised to 10 into, we are finding with respect to y. So here you can see it is going to be y raised to 6. So I'll be having here this 6 x cube y raised to 5 minus x cube y raised to 6, and here we'll be having 10 y raised to 9 upon x raised to 6 plus y raised to 10 bracket square. Okay. Now let us find with respect to x. So dabba v by dabba x is equal to x raised to 6 y raised to 10. Then I'll be having 3x square y raised to 6 minus x cube y raised to 6, and here I'll be having 6 x raised to 5 upon x raised to 6 y raised to 10 bracket square. And now we know where we have to find out these conditions. Okay, so these conditions we have to test that z is equal to 0. Okay, so these conditions we have to test that z is equal to 0. So what I'll be having is at z is equal to 0, that is x is equal to 0 and y is equal to 0. So what you get is w by w x is equal to 0, w by w y is equal to 0, w by w x is equal to 0, w by w y is equal to 0. So now see, and hence we have w by w x is equal to w by w y, and w by w y is equal to minus w by w x. So that is, we say CR equations are satisfied. As 0 is same as minus 0, so these conditions are satisfied. Now can you tell me whether they are continuous? So see these conditions, w by w x is equal to 0, w by w y is equal to 0, w by w x is equal to 0, and w by w y is equal to 0. So we have to test these first order derivatives whether they are continuous or not. So are they continuous? So what do you think? Are these first order derivatives at 0 continuous? So these are the point functions basically. Okay. So these are the point functions, and hence these are not continuous. So continuity cannot be tested here, and that's why though this is satisfied, we cannot guarantee that whether the function is going to be analytic or not. And now if we want to show that the function is not analytic, then we have to consider the another way to find the derivative. Okay, so we have limit z tends to 0. Okay, f of z minus f at 0 upon z minus 0. So if this limit exists, then the function is differentiable. If this limit does not exist, then the function is not differentiable. So limit z tends to 0. Here we have x cubed y raised to 5 x plus iy upon x raised to 6 y raised to 10 minus 0 upon z is x plus iy minus 0. So this is limit z tends to 0 x raised to 5 by x cube. Okay, so we have x cube y raised to 5 upon x raised to 6 and y raised to 10. Okay, so what we got here? We got this is limit. Now as z tends to 0, so z tends to 0, this implies x tends to 0 and y tends to 0. So here we have x tends to 0 and y tends to 0. So this is x cube into y raised to 5 upon x raised to 6 plus y raised to 10. So this is called simultaneous limit. Okay, so we have to solve now simultaneous limit. So limit x tends to 0, y tends to 0, x cube y raised to 5. And if you see the denominator, it is x cube square and y raised to 5 square. So that means, okay, so if I want to have this solution for this simultaneous limit, then I have to relate. So there is some relation between x cube and y raised to 5. Okay, so what can be the relation? The first relation, x cube is equal to my raised to 5, or the second relation, okay, mx cube is equal to y raised to 5. So either of this relation we can have. Okay, and now either of this relation we can choose, and we can see as x goes 0, y will also go to 0, or as y goes 0, x will also go to 0. So these two relations will satisfy the simultaneous the condition for the simultaneous limit, and hence we put, okay, so either of this is possible. So I am putting x cube is equal to y raised to 5, and since x tends to 0 implies that y also will go to 0. Okay, so we get what we are finding. We are finding limit z tends to 0 f of z minus f of 0 upon z minus 0. This is our limit that we are calculating. So here we get limit y tends to 0. X I am replacing in terms of y now. So it is my raised to 5 y raised to 5. And here I'll be having my raised to 5 square plus y raised to 10. So let us simplify this. We get, okay, this is equal to limit y tends to 0 y raised to 10. This is square y raised to 10 plus y raised to 10. So we can write limit y tends to 0 y raised to 10 m. So I am getting here y raised to 10 1 plus m square, and so this will get cancelled. So I will have limit y tends to 0 m upon m square plus 1. So this is what we'll be having, limit z tends to 0 f of z minus f at 0 upon z minus 0. Okay, or this is m upon m square plus 1. So you got limit z tends to 0 f of z minus f of 0 upon z minus 0, and this is equal to m upon m square plus 1. So what we can say is the above limit depends on m, that is the path, okay, and hence does not exist. So this limit does not exist, that is f dash of z at z is equal to 0 does not exist. So if does not exist, that means it is not differentiable. So that is f of z is not differentiable at z is equal to 0. And hence we can say f of z is not analytic at z is equal to 0. So the condition that it has to be differentiable, then only it will be analytic. So this was only function, only a point where we have to test, and that's why we tested the derivative exists or not. So derivative at this point does not exist, and hence it is not going to be an analytic function. Okay. So do you have any doubt in this example? I hope you don't have any doubt. Okay, that's good. No problem. So if you don't have any doubt, that's good. Okay.